I'm Mark Cavanaugh for Cavi Coaches, and today I'm going to coach you up on using velocity time graphs to solve kinematic problems. Today we're going to look at using velocity time graphs to solve kinematic problems. How can we use that? Well, we can use them in lieu of the kinematic equations. So we're going to draw a velocity time graph, just an arbitrary graph, where we have a line that shows that the object is speeding up. Now we're going to list our 6 variables, and we're going to find all 6 variables using this graph. The initial velocity is the y-intercept. The final velocity is the final value on the vertical axis. The time we can find just using the value along the horizontal axis. Now we can also look at the rise, which is the change in velocity, over the run, which is the change in time. What change in velocity over change in time? Well, that's the slope of the line, and that's also acceleration. So the acceleration is the slope of a velocity time graph. Now we can also look at position, but initial and final position are not going to be found on the graph, but we can find a change in position. And the way we find a change in position is by finding the area. So we have the area of a rectangle and a triangle, we add those together, and that equals the change in position. So the area is under the curve is the change in position. Now don't get alarmed. Yes, I know it's a line, but we call it a curve even though it's a line. All graphs are considered curves. So let's use a velocity time graph to solve the same 3 questions we used in the previous video. So we have the same car exiting the highway at 35 miles per hour, 30 meters per second, and it comes to a stop in 5 seconds. We want to know the acceleration. Well, we're going to draw our velocity time graph. And our velocity time graph is showing that the car, is slowing to a stop. So it shows us a negatively sloped line. Remember, velocity time graphs are always some version of a line in an algebra-based physics course if you are asked to draw it. So we have our initial velocity of 30, took 5 seconds to come to a stop, and we're asked the acceleration. The acceleration is just the slope of the line. So I can find the slope. Change in velocity is negative 30. The change in time is 5 seconds. And I know the basic definition of slope is rise over run. So I can set my rise is negative 30, my run is 5, and that gives me an acceleration, which is my slope, of negative 6 meters per second squared. Now you might be saying right now, wow, that was a lot easier than using the kinematic equations, and you might be right, but you might be more comfortable using the equations than having to draw a graph. So you really just have to pick. So let's look at the second example. As the car exits the highway, now we want to know how far did the car travel while braking. So we have our same graph starting at 30 meters per second, ending at 0 in 5 seconds. And how far is asking for the displacement or the change in position, which is just the area under the curve. So we have this triangle, and the area of a triangle is just 1/2 base times height, 1/2 of 30 times 5. We can see that the units cancel out here. The 30 times 5, the seconds cancel, leaving us with meters, which is the unit we have for position, and we get change in x is 75 meters. Now again, you might be thinking, oh my goodness, that was incredibly easy compared to using the kinematic equations. And again, you might be right, but it's just a comfort level. Do you feel comfortable drawing velocity time graphs? So let's look at the third example that we did, the one with the sprinter, where the sprinter was speeding up. So we're going to draw a velocity time graph for the world-class sprinter problem. So we draw the velocity time graph, and this one shows that the sprinter is speeding up and reaches a speed of 11.7 meters per second. And what we're being asked is how far did the sprinter run while speeding up? So how far is asking for the displacement or change in position, and the change in position is just the area under the curve. The problem that we have, though, is that we don't know the time for the base of our triangle. So what we're going to have to do is we're going to have to use some extra information, extra pieces of the velocity time graph to determine the time first. So this 3.8 meters per second each second we've defined as the acceleration. What do we know? That the acceleration is the slope of the line. So acceleration is just change in velocity over change in time, rise over run. So we can rearrange this equation to solve for time, and we can plug in our change in velocity, which is going to be going from 0 to 11.7. So 11.7 minus 0 gives us 11.7 divided by 3.8. We can see that meters cancel out. The seconds cancel out one of them, leaving us with 1 over inverse seconds, which is a unit of seconds. And we can see that it takes 3.08 seconds for the sprinter to reach maximum speed, which now we can put on our graph. Now we can take this graph and how far did the sprinter run? Well, that's just the area under the curve. Now we have the base and the height, and we can find the base and height. X is equal to 1/2 base times height, and that's 1/2 of 11.7 times 3.08. We can cancel out seconds in our units, leaving us with meters, and find that it's 18.02 meters. Now, you might look at this question and say, that was a lot more complicated to use the velocity time graph. And you're probably right. The kinematic equation was a one-step problem using the process that I showed you. In this case, we had to do a two-step problem where we had to find time, which is the base of our triangle, before we found the area of that triangle. So you can use kinematics in multiple ways, either the equations or the velocity time graphs. Sometimes the velocity time graphs are easier to use, sometimes the equations are easier to use. You just have to pick. This is how you use velocity time graphs to solve kinematic equations. I hope this is helpful. Have a great day and an even better tomorrow.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.